Hello, welcome you all for this new video session on the shaft. Okay, in this video session we will see derivation of the shape function for the shaft element. Also we will derive the stiffness matrix of the shaft element. What is shaft? Shaft, it is a circular member which is used to transmit the power from one element to another. Okay, what is torsion? Torsion means it is a turning force applied at the cross section. In other words, it is a force it is required to twist a member. Okay, it is a force required to twist a machine member. Already we have studied the torsion of shaft in the mechanics of materials, where we have derived the torsion equation, that is T by J equal to tau by R, that is equal to G theta by L. Okay, where T is the torsional moment, J is the polar moment of inertia, tau is the shear stress, R is the radius of curvature, and G is the modulus of rigidity, theta is the angle of twist, and L is the length of the shaft. Okay, when the torque is applied or the torsional moment is applied, there is angle of twist in the shaft, that is theta. Okay, in these derivations there are some assumptions are there. Okay, these are the assumptions made to derive this equation. This is the torsion equation. We are using this equation to derive the stiffness matrix of the element. Okay, let us go to shape functions. Let us find the shape functions for the shaft element. Okay, the derivation of this shape function and to the derivation of the stiffness matrix, it is just similar to the bar element. Okay, you can see the finite element formulations here. Okay, it is a it is a shaft element. It is a shaft element which has two nodes. When the torque is applied, this nodal displacement, it is the angular, it is or the twist at node 1, that is pi 1, or the twist at node 2, that is pi 2. Okay, the analysis which is similar to the bars problem. Okay, as we know two boundary condition at x is equal to x1, we are deriving the shape function in terms of global coordinate systems. At x is equal to x1, angle of twist, that is pi is equal to pi 1. At x is equal to x2, it is pi is equal to pi 2. As we know two boundary conditions or two nodal displacement, let us use a linear element, that is pi is equal to a0 plus a1x. Pi is equal to a0 plus a1x. This is the interpolation function or the displacement functions it is assumed. Okay, applying the boundary conditions here, at x is equal to x1, pi is equal to pi 1. Substituting x value and pi value in this function, we have this equation. Similarly, applying the second boundary condition, simplifying this and finding the constants a0 and a1. It is explained here how to find the a0 and a1. Okay, we have a0 is equal to phi 1 x2 minus phi 2 x1 divided by x2 minus x1, and a1 is phi 2 minus phi 1 divided by x2 minus x1. Okay, substituting the value of a0 and a1, substituting the value of a0. Okay, this is the displacement equation. By applying the boundary condition, that is at x is equal to x1, you substitute x1 here and it is phi 1. This is one equation. And the second boundary condition, where x is equal to x2 and phi is equal to pi 2. Now we have two equations and two constant. Okay, simplify and find a0 and a1. Okay, after finding a0 a1, you substitute the value of a0 and a1 in these equations. Okay, see here, a0, this is a0 and this is a1. Okay, then phi 1 x2 minus phi 2 x1 plus phi 2 x minus phi 1 x. Okay, where phi 1 and phi 2 are the angle of twist at node 1 and node 2. Already we know that to express the displacement at any node, if you are using the shape functions, we can calculate the angle of twist at any node. Okay, we are using the shape functions to find the angle of twist at any point within the shaft element. So what is the coefficient of this phi 1? Okay, this represents the shape function 1. Okay, that is at node 1. Okay, then the coefficient of phi 2, how this phi 1 and how this value comes. Okay, let us see what is the coefficient of phi 1 here. It is x2. Okay, one more phi 1 it is here, so you take pi 1 outside, so pi 1 is into x2 minus x divided by x2 minus x1. Okay, similar fashion the coefficient of phi 2, there are two pi 2 terms, pi 2 equal to minus x1 plus x, so or in other words x minus x1, x minus x1 divided by x2 minus x1. So the coefficient of phi 1 it is n1, the coefficient of phi 2 is equal to n2. Okay, to find displacement, that is angle of twist at any point within the shaft element, we are using the shape functions n1 and n2, where pi 1 and pi 2 are the nodal displacement at node 1 and node 2, that is angle of twist at node 1 and node 2. Okay, these are the shape functions. Okay, these are the shape functions in terms of global or Cartesian coordinate system. We already know how to derive the shape functions for the bar element. The analysis of the bar and shaft, it is almost same. Already we have derived the shape functions for the bar element. N1 is equal to 1 minus zeta by 2, N2 is equal to 1 plus zeta by 2. How it is derived? We have taken again the same equations, same displacement equation, but there it is a0 plus a1 zeta. What is the zeta value? Zeta is minus 1 at node 1, zeta is plus 1 at node 2. Okay, applying the two boundary conditions, we have n1 is equal to 1 minus zeta by 2, n2 is equal to 1 plus zeta by 2. It is in terms of a natural coordinate system. Okay, the analysis is same. We also derived the strain displacement matrix. Okay, that is equal to 1 by LE minus 1 1. Okay, it is also same for the torsion of shaft roll. Now this is a shaft. When a turning moment is applied, there is a twist. Okay, what is the effect of this twist? Let us see. This point B changes its position to B dash. So what is the angle of change, or it is the twist, angle of twist, it is pi. Okay, by this arc we can say that the angle of twist is equal to r pi. Okay, r pi. Okay, it is we already know the torsion equation, T by J equal to tau by R equal to G theta by L, where T is equal to torque, J is polar moment of inertia, tau is shear stress, R is radius of curvature, G is modulus of rigidity, theta is angle of twist, and L is the length of the shaft. When the turning moment is applied, there is angle of twist throughout the length. Okay, the angle of twist at node 1 it is phi 1, angle of twist at node 2 is phi 2. Okay, for the derivation purpose we have considered the angle of twist phi 1 is equal to 0, but in real practical cases it is not 0 here, because the torsion it is applied at both ends. Okay, we will derive the stiffness matrix of this shaft element in the next video sessions. Okay, in this session we have derived the shape functions for this shaft element in terms of global or Cartesian coordinates. Okay, it is already derived the shape function in terms of natural coordinates for the bar element. Okay, the same procedure follows for this shaft element. Okay, and this is also same. This is strain displacement matrix. What we have derived for the bar element, it is same for the shaft element. Okay, in the next video session we will see the stiffness matrix of the shaft element. Okay, the shape function is derived in this session. Shape function n1 is equal to 1 minus zeta by 2, n2 is equal to 1 plus zeta by 2 in terms of a local coordinate system. Okay, in terms of global coordinate system it is expressed with respect to x, x1 and x2. These are the shape functions in terms of a global or